So everyone just remember that I'm going to post the solutions for assignment 1B today. I just waited a few days to give people some extra time. There were some requests. And then for assignment 1C, I believe we're going to be taking that up next Tuesday. So it has to be in by then at the latest. That's all the assignments we're doing for this particular chapter. And then at the end of this lesson, I think we'll tentatively schedule the first test date. Okay, let's see. So today we are doing integration by trigonometric substitution. So that's 28.8. And I like this section because this is one of the questions where it's like kind of like solving a fun puzzle. Although these questions could kind of go on forever and they could be a little bit complicated. So they're not like a fan favorite among students. But I don't think they're too bad. Let's see, still recording, good. And I'm just going to use a whiteboard probably for this whole thing. Okay, so trigonometric, sorry?
Is there any chance the fire alarm's still going off over there?
Yes, it is.
Is there any chance you can wait for Cam as he doesn't feel comfortable entering the school until it's cleared?
Well, this is all being recorded, so anything that he misses, he'll be able to catch up on. And right. Hopefully he'll be able to join in maybe on his phone. Yeah, but it's all being recorded, so I think he'll be okay with me starting. Okay, and hopefully it'll stop soon. Okay, let's see. Did Cam make that request specifically, or I'm just curious. Okay, well, yeah, we'll just keep going. Okay, so integration by trigonometric substitution. So this is where you have an algebraic integral that you want to solve that you can't solve by any of the previous methods. Sometimes it looks like you can, but you can't. And in this case, you use trig substitution, which basically means you substitute a trig function into the integral, and then you just work solving the integral based on using trigonometry. And then at the end, you switch it back to an algebraic answer. So it's kind of like sidestepping the problem. So it's like, okay, we have this algebraic integral, we can't solve it, so we'll kind of turn it into trig, solve it, and then we'll regress back into algebra. So there's a list of substitutions that you'll have to know, and it's in the textbook. Let me just, hold on. Okay, let's see what we have. So it says if the integral involves, so the first one is square root of a squared minus x squared. So if your integral involves that, you do a particular substitution, and it is x is equal to a sine theta. And then it also gives you an identity that you can use. So yeah, again, this is all in a chart. It's on page 876. So 1 minus, so this is the identity that you'll use. 1 minus sine squared theta equals cos squared theta. So that's a pretty common identity. It's, sine squared theta plus cos squared theta equals 1, and it's just rearranged a little bit. And then it says to rewrite radical as a cos theta, but I don't find that particular column helpful because, yeah, the question's going to unfold in that direction regardless. So this is what you do when there's a minus sign, specifically in this case. And then when there's a plus sign, so square root of a squared plus x squared. In this case, for this one, you use x equals a tan theta. So remember, for this one, you have a squared within your square root, but you specifically use a for the substitution. So that's just be aware of that. And then it also gives you a helpful trig identity, which is 1 plus tan squared theta equals secant squared theta. And then the last one is x square root of x squared minus a squared. And for that one, you use secant. So x equals a secant theta. And then for the trig identity that it gives you, you can use secant. And of course, we'll go through a bunch of questions. At this point, none of this is overly overly useful without actually seeing specific questions. But I just thought I'd outline this, and that is the identity that you can use. And then has a couple of other things that it mentions. It says replace all factors of the integral with expressions in terms of theta, thus obtaining a trigonometric integral. Integrate the trigonometric integral. Geez, they really had to clarify that. Integrate the integral, that's good advice. Number 4, express the answer in terms of the original variable x. So it's basically what I said, that you're taking algebra, turning it into trig, and then putting it back in terms of algebra. So let's look at a particular example. And I think I'm going to have to erase this, but again, it's in the textbook and it's also in the PowerPoint. And maybe I'll keep, actually for this one, I'll keep the first row because we're going to have to use that row. So let's erase everything else. Okay, so this is example number 1. Okay, let's try to be economic with the whiteboard here because I always run out of room. So I'll try to do this on the left. Okay, so integral of dx over x squared and then square root of 1 minus x squared. So if you look at this integral, a lot of people, including me, would probably try to initially just do an inverse trig function because it kind of looks like you could do that. But there's an x squared at the bottom, and that messes everything up. That x squared, you can't get rid of it. You can't move it outside the integral. So it disqualifies the use of inverse trig functions, unfortunately, which are a lot easier. Okay, so in this case, let's follow the steps that it outlined. Let's just start with what form we have to use. So you have 1 minus x squared. So that's in the form a squared minus x squared. In this case, a squared is just 1. 1 is the same as 1 squared. So we use the substitution from the first row, which is x equals a sine theta. So let's do that substitution. X equals, and a in this case is just, so I'll just write x equals a sine, actually, hold on. For convenience later on, I'll just directly write it. Let's erase this. So yeah, a in this case is 1. So your substitution is going to be x equals 1 sine theta, or you could just write sine theta, same thing. So a pretty simple substitution in this case, since a is just 1. So that's the substitution that it tells you to do. And then from this point on, basically what you do is pretty much what you would expect. You kind of just take that and you collect everything that happens to be in the integral. So you figure out what is the square root of 1 minus x squared in terms of sine theta. You figure out what is x squared in terms of sine theta. And you even figure out what is dx in terms of sine theta. You just go through them one at a time and just figure them out, simplify them as much as possible, and then just shove everything into the integral. And then you'll simplify stuff and you'll be able to solve it. So let's just do this one step at a time. So it's finished, the fire alarm is off. Okie doke, let's see. So which one should we do first? So for x squared, that's just gonna be sine squared. I don't think that's even, there's no point in writing that separately. We'll just do that when we plug it in. Let's do the square root part because you gotta do some trickery there. So square root of 1 minus x squared. And then what you do is you substitute sine theta in for x. So that will be the square root of 1 minus sine theta squared. And then if you'll notice, this is the same expression that they had listed on the top. It was a suggestion for a trig identity that you can use in this case. So in this case, we're going to take 1 minus sine theta and just replace it with cos squared theta. So inside your square root, so we're just using this right here. So that's going to be cos squared theta. And now this part simplifies really nicely because you have the square root of something squared. So of course, the square root of cos squared theta is just cos theta. So that's that usually happens in these questions where it kind of simplifies very nicely and you know that you're on the right track. What else do we need? Dx, we need dx as well. So dx is just going to be the derivative of x. So the derivative of sine is cos. So that part's just cos. What else do we need? I guess that's everything. So yeah, now we just plug everything into our integral. So this will be on top will be dx, which is cos theta. On the bottom, you have x squared, so that'll be sine squared. And then the whole square root part, we already figured that whole part out. That ends up just being cos theta. And you don't need a square root in this case because we already took that into consideration when we figured it out off to the side. So the square root of 1 minus x squared, the whole thing was just cos theta. And now again, oh, sorry, I should have a d theta in here. Yeah, dx equals cos theta, and then you should have this little d theta, and you should have this as well, because every integral needs the d part. Okay, so now you'll probably notice, again, some nice cancellation happens. You have a cos on top, and you have a cos on the bottom, so you can cancel those. So goodbye, goodbye. And then we get integral of d theta over sine squared theta. And at this point, it's actually pretty easy to solve. So this is just, you could substitute in its reciprocal function, right? The reciprocal function of sine is cosecant. So this is the same thing as the integral of cosecant squared. You could always do that when something's on the bottom, you could bring it up to the top as long as you just change it to its reciprocal function. So let's do that. So this will be cosecant squared theta d theta. And now at this point, this particular integral is just listed in one of the previous sections. It's listed as the integral of this is minus cotangent theta plus our constant. So minus cotangent theta plus our constant. Yeah, that's just listed in, what section was that? It was 28 point, I think it was 28.4, the basic trigonometric forms. Okay, so we've solved our question. It's not too bad, but unfortunately we're not quite done yet. So yeah, like I said, these go on a bit long. So the problem here is that your original integral was entirely in terms of x. It was just an algebraic expression. But now your answer is entirely in terms of trig, and it doesn't even have the same variable because trig has theta, which represents an angle. So in this case, what you have to do is you have to figure out a way to take your minus cotangent theta and rewrite it so that it's entirely in terms of x. And there's a couple of things you need here. You need SOHCAHTOA. So let's write that on top. SOHCAHTOA. You also need the Pythagorean theorem, which is, see if I could squeeze this in right here. So this is regarding the sides of a right triangle. So those are 90-degree angle right here. And we could label these A, B, and C. And the formula is that A squared plus B squared equals C squared. So this is all just generic trig stuff. Like the Pythagorean theorem is like literally 2,000 years old. So this is just some stuff we're going to have to use in a minute. Okay, so what do? How do we rewrite this in terms of x? Okay, what you're going to do is you're going to take your original statement, your original substitution statement, which is this right here. And you're going to construct a special triangle using that statement. We've seen special triangles before. We've seen 2 of them, but those were just like generic pre-existing special triangles. In this case, you're going to create one just for this question, just based on that one statement. And this is the part where everyone gets stuck because there's so much stuff flying around and everything. So just remember that for this part, you always just use the original substitution that you have. Okay, so how do we construct a triangle in this case? So we just use SOHCAHTOA. So let's just take the substitution. We have sine theta equals x. And now what I'm going to do, because usually like sine is opposite over hypotenuse, so I'm just going to write this as x over 1. Because yeah, just to give, it's a logical way to write it. Otherwise, there's no bottom number and it's kind of confusing. So according to SOHCAHTOA, sine is opposite over hypotenuse. So what you do is you just draw a triangle where x is the opposite side, 1 is the hypotenuse side, and then you can use the Pythagorean theorem to deduce the third side. And then you'll almost be done the question. So let's try to fit this in without erasing anything. Okay, and you got to be careful at this point as well. Okay, so how should we label this? There's such limited room. Okay, so let's label these. So let's pick our angle as, let me just see what they do in the textbook. I'll do the same thing that they do. Yeah, I don't like what they do, but I'll do that anyways. Let me just rewrite this a little bit. Okay, so yeah, they just kind of write it in a bit of a backwards way. So pretend that's a 90-degree angle. It's not very well drawn. Okay, and now let me draw. So we're going to pick a theta. So you can't pick the 90-degree angle, but you could pick any of the other angles. It literally doesn't matter. So you just draw a theta right here because you need an angle in reference to what you're doing. Okay, so it said, and now let's just label everything as opposite, hypotenuse, and adjacent before we do anything else. Okay, opposite is this one. Hypotenuse is always this one. And adjacent is this one. Okay, so far so good. And now you just insert x and 1 at their appropriate places. Make sure you put them where they belong, because a lot of people will just toss them anywhere, but like x in this case specifically corresponds with the opposite side. So this is x, that side right there. So you got to put things where they belong. And then the 1 is hypotenuse, according to this right here. 1 equals hypotenuse. Okay, so this might seem like we're going down like a rabbit hole and it's not going to help us solve this, but once we get all these sides, then what we can do is we can write cotangent in terms of x, because this entire triangle will be in terms of x. Adjacent, now we have to figure out adjacent. And what are we going to use? We're going to use the Pythagorean theorem. So let's, there's such limited room. Let me just label this as, let's do A, B, and C. So too many labels, but I'm trying my best. And the Pythagorean theorem is a squared plus b squared equals c squared. Okay, and again, just take your x and your 1 and sub it into this equation. Make sure you plug them in where they belong. People have a habit of just plugging everything into the left side, regardless of what the variables are, but that's not how algebra works. Like for example, in this case, c happens to be 1, so you'll plug 1 in where c is. You'll plug it in on the right side. And then x happens to be b, so that's where you'll put x, and then you'll solve for the remaining one, which is a. So in this case, you have to put things, where the corresponding variables actually are. You can't just conveniently shove everything into one side of the equation. You got to be careful. Okay, so a squared is just a squared for now. B squared is x squared. And c squared is 1 squared, so that's just 1. And now you rearrange this and get a by itself. So let's do that. So to rearrange this, this is just some basic algebra, take the plus x squared part, move it to the other side and change it to minus x squared. So you got a squared equals 1 minus x squared. And then you just square root each side to get a by itself. So square root. So a is the square root of 1 minus x squared. And ironically, it's in the original integral that for some reason seems to happen with probably every question, where this part right here, maybe by coincidence or maybe by some whatever specific reason, is part of your original integral. But yeah, it doesn't really matter beyond that. It's just kind of a curiosity. Okay, so this side is square root of 1 minus x squared. Okay, so at this point, everyone's probably like, what the heck was the point of doing this? Well, now we can write cotangent in terms of all of these sides. So we just use SOHCAHTOA again. So I'll put the minus sign right here. That'll just sit there. Cotangent is, so tangent is opposite over adjacent. So cotangent will be the flip of that. It'll be adjacent over opposite. So let's write that. So minus adjacent over opposite. And then you just plug in whatever that is. So what is adjacent? That was square root of 1 minus x squared over, and then opposite was, I'm just doing this according to these labels right here. Opposite was x. Oh, and the minus sign is still there. Opposite was x, and then you have plus your constant. So that right there is your final answer for this question. So the integral is equal to minus square root of 1 minus x squared over x plus your constant. So like I said, I don't mind these because they're like solving little puzzles, and they're not bad if you have some basic trig knowledge. Like you have to really know how SOHCAHTOA functions and what SOHCAHTOA is. It's of course, it's basically giving you the definition of the basic trig functions. Sine is opposite over hypotenuse, cos is adjacent over hypotenuse, et cetera, et cetera. So you have to know that. You have to know the Pythagorean theorem. You have to know some basic algebra and how to manipulate equations. And yeah, so these can be pretty long and pretty weird, but yeah, overall they're not, I don't think they're too bad. Let's see. So let's do one of each because there's 3 different substitutions. So let's do the next one. And we are still recording, yes. Okay, let's get rid of this. And maybe I should write out the second row because that's what we're going to use for this. So this is where it's in the form of a squared plus x squared. You use the substitution x equals a tan theta. And you use the trig identity 1 plus tan squared theta equals secant squared theta. Okay, so the actual question is integral of dx over square root of x squared plus 4. And again, this one looks like one where you could use an inverse trig function. And let me look at the inverse, like I'm just gonna check why is it that we can't in this case? It's probably just because it happens to be slightly different than the form that you would need. Where are the inverse trig functions? I'm just looking at this for my own curiosity. Yeah, the sine inverse function has a minus sign at the bottom, and the 2 variables would have to be switched. So an inverse function, sine inverse function wouldn't work. And then the tan inverse function doesn't even have a square root. So that's the first thing that I would check in this case, because it looks like you might be able to use one of those previous functions, but no, it doesn't work. Okay, our substitution, in this case, a squared is 4. So a is 2. So x is going to be 2 tan theta. So good. And again, make sure it again, in this case, you have a 4 in the expression, but that's a squared. And then in the actual substitution, you just use a. So that's why I'm just using 2. Okay, what to do. So now we have our substitution, and now we want to, again, collect everything that we have that we need in the integral. So let's just do the square root part first. Square root of x squared plus 4. So that will equal the square root of x is 2 tan theta. So it'll be 2 tan theta squared plus 4. Good. So far, so good. Now, 2 tan theta squared is the same thing as 2 squared times tan squared. You could kind of distribute the square to each of them. So that's what we're going to do. Everything else will just stay the same. So this will be 4 tan squared theta plus 4. And now at this point, I think what I would do is, since there's a 4 in each of these terms, I would probably factor out this 4. and kind of just, yeah, that seems like the logical thing to do. So let's factor it out. And what you could do is actually something really cool. Here, let's just do the factoring part first. So square root of 4 bracket, and then you'll just have tan squared theta plus 1. So I just took the 4 out of each term. And now the cool thing is that when it comes to multiplication, you can separate square roots. So you could actually break this square root into 2, and you could have it just around the 4, square root of 4, and then you could have it just around the rest of it, which is tan squared theta plus 1. So that's a really cool trick. It only works in some cases. It only works with multiplication. It doesn't work with addition. So yeah, you can only break it apart where it's something times something within the square root. And now we can simplify this really, really nicely. Square root of 4 is 2. And then within the square root, now we use this substitution. So the thing in the square root, we're going to substitute it for secant squared theta. So even as you look at the second question, you can see that these all kind of just follow the same pattern. It's do a substitution, figure out the square root part, figure out anything else in the expression, and then plug it all in. So again, a really nice cancellation happens here. You have secant squared, square rooted. So this is just going to be 2 secant theta. Okay, is that right? Yes. So far, so good. And what else do we need? dx. We also need the dx part. So that will be, so if x is 2 tan theta, dx will be 2, what's the derivative of tan? It's secant squared, right? Yes. So derivative is secant squared theta d theta. So that's the only other thing you need in this case. And now you just substitute everything into your integral. So on top is dx. So that is 2 secant squared theta d theta. And then at the bottom, the whole square root we figured out was 2 secant theta. Ooh, that's really nice. Some nice cancellation there. Okay, so that's good. So the 2 and the 2 obviously cancel out. I'd get rid of those. And it looks like, oh, sorry, at the bottom, it should just be secant. Sorry, I accidentally wrote secant squared. Yeah, because that part, if you look on the right, it's just 2 secant that we figured out. I'll just rewrite that. 2, or yeah, secant theta. Okay, and now you could do a little more cancellation. You have a secant squared on top and a secant on the bottom. So you could partially cancel those out and you'll just get a secant on top. So basically this goes away and this just turns to 1, or just standard secant. So integral of secant theta d theta. Okay, again, so far so good. And now we have to integrate this. And again, it's just listed in a previous section where it lists all of the standard common trig integrals. This one's a bit of an ugly one. You get, let's see, you get the ln of absolute value of secant theta plus tan theta plus your constant. So this one definitely sucks because you have secant and tan. So like it's a little extra work. You don't have to do 2 triangles, you just have to do 1. That's the good news at least, because you just do it based on the original substitution, and then the triangle will apply to both secant and tan, of course. So we go through the same process as before. And again, this is the one part where everyone's like, I give up, there's too much stuff, I don't know what to do. So always just remember, make a note of it, go back to your original substitution. And that's how you'll get your special triangle. So let's do x equals 2 tan theta. And we just want tan theta equals whatever. So let's take the 2 and move it over to the other side and change it to division. And I'm just going to write it like this for convenience. So so tan theta equals x over 2. Yeah, again, remember that with manipulating algebraic expressions, like it's 2 times tan theta. So when you move it over, you have to change it from multiplication to division. That's the case in any algebraic expression when you're moving stuff from one side to the other. Okay, let's break out the SOHCAHTOA. Let's do that over here. SOHCAHTOA. Okay, tan is opposite over adjacent. So let's write that in here. And you got to be really careful because there's a lot of different mistakes you can make. Opposite over adjacent. So now let's construct a triangle that has x as the opposite end and 2 as the adjacent end. Where should we do this? Maybe we'll do this on top right here. Special triangle, always a 90-degree angle. And then you just pick theta wherever you want. You can use the left one or the top angle, doesn't matter. So I'll just put theta right here. Okay, and now let's put everything in here. X is opposite. So the opposite is this one right here. 2 is adjacent. Adjacent is just the one that's touching the angle that isn't the hypotenuse. So 2 is adjacent. And now we have to use the Pythagorean theorem to solve for the remaining side. So like with the Pythagorean theorem, be careful because sometimes you'll be solving for a squared or solving for a or solving for b or solving for c. It just depends on what the circumstances are. You just do whatever the question leads you to do. So yeah, so this is right here. This is c. Okay, so what was our Pythagorean theorem? It was a squared plus b squared equals c squared. Okay, and let's label this. So 2 can be a, x is b, and then c is unknown. Okay, so a squared plus b squared equals c squared. So a squared will be 2 squared plus b squared will be x squared, and that equals c squared. So this one's a little bit different than the previous one. It'll require a little less rearranging. And now, of course, 4 squared or 2 squared is 4. So that's 4 plus x squared. And then, of course, you could square root each side to get c by itself. So to save room, I'll just do that kind of simultaneously right here. And that is c. And that looks right. Yeah, same thing they have in the textbook. Now you can finally write your answer in terms entirely of x's, because now you have a, b, and c. So let's do this. So this is, so ln absolute value. So secant is, what is secant again? That's the inverse of cos. So that's going to be hypotenuse over adjacent, because cos is adjacent over hypotenuse. So for its reciprocal function, you just switch them. So maybe for clarity, I should write that hypotenuse. This is a bad way to write it, but here I'll just write it. Hypotenuse over adjacent will be that part plus, and then tan theta is opposite over adjacent. Opposite over adjacent. Yeah, not a great way to write it, but just again, so people don't get confused about where I'm getting everything from. Okay, now let's substitute everything in, every specific thing in. Hypotenuse is c. That's square root of 4 plus x squared. Square root of 4 plus x squared over, and then adjacent is 2 over 2 plus, and next one, opposite over adjacent. So opposite here is, x over, and then adjacent is still just 2 plus c. So that is your final answer. And is there any way of simplifying this one? Yes, there is. Let's see if that's even worth it. So we have, yeah, you could simplify this. Yeah, let's fully simplify this just for the sake of completing it. Let's clear some of this, because the simplification for this is actually pretty cool. All it is just doing some ln stuff and just kind of doing some superficial simplifying. But we have the answer, so we could pretty much erase everything else. Okay, let's make some room. Okay, we don't need this anymore. Okay. Okay, so for simplifying this, first thing I would do is notice that you have two terms in your ln, and there's a 2 on the bottom of each of them, so you have a common denominator. So you can combine the two terms into one fraction. So let's start with that. So this will be ln of absolute value, and then on top you'll get square root of 4 plus x squared plus x, and you could put everything over 2 plus c. And now what you can do is you can use a rule that when you have division within ln, you could split the lns, but you change it into subtraction. So here's the rule. Here, I'll write this at the top. Here's the generic rule. Ln of x over y equals ln of x minus ln of y. So you can separate the two things as long as you change it from division to subtraction. So in this case, let's do that. So it'll be ln of the top minus ln of the bottom, which is just ln of 2. And then you could do something kind of cool. So ln of absolute value square root 4 plus x squared plus x and absolute value, and then minus, and then ln of 2 plus c. And the reason this is a cool simplification is because now you could take this part right here and combine them into one term. Because think about it, c is an arbitrary constant, and subtracting ln of 2 is also just, it's a particular number. So if you have like an arbitrary constant minus a particular number, guess what you get? You just get an arbitrary constant. So in this case, you could literally just remove the minus ln of 2, but you do have to change the c because it's not the same arbitrary constant, it's different. So what I would do is I would just substitute in like just c prime or something like that. Just here, we'll complete it right here. So ln absolute value, blah, 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 4 plus x squared plus x. And then we'll just write plus c prime. So yeah, again, I'm just kind of combining those two numbers into one, but to use proper notation, we should not use c again, because this new constant is a little bit different from c. So sometimes you do stuff like that, where it's like, okay, we could simplify the answer in this way. So it's a really cool simplification because it really does make the answer look a lot better. What are they using? Okay, yeah, in the textbook, they just use c prime as well. Okay, let's see. Maybe we'll take a bit of an early, let me just see how many questions there are. Actually, there's only one more that I really want to do. So maybe we'll just do that one and then we'll call it a day. Yeah, and then I'll give a participation question for this one as well. Oh, we got a chat. Oh, someone has a good question. Doesn't the prime symbol usually mean taking the derivative, or is it used for a lot of different things? In this case, the answer is yes. It is used for derivatives, but in this case, it's just used just to denote that it's different from c. Like in this case, you could use d, you could use e, you could use any symbol you want, but c prime is just kind of a standard thing to use. And from the context, hopefully it's clear that you're not taking the derivative of it, because the derivative would be 0 regardless. So yeah, in this, good question, but in this case, it's just basically renaming c into something else. Okay, let's do example number 3, which is also interesting because you don't need a special triangle at the end of this one, which is initially weird and confusing, but then, I mean, it's easier. So it's like, it's hard to complain.
Before you move on, can you just explain what you did to get the integral of secant to d theta? Or is it secant theta d theta or whatever that is there?
Secant theta d, I'm just wondering where we are in the question. Oh, like right here?
Yeah, right there.
Okay, so here, let's look at the original the original integral, it is square root, integral of dx over square root of x squared plus 4. So what we did was we used the substitution x equals 2, tan theta. And then we derived everything that we needed from there. So we eventually found out, and if you want, you could just refer. I don't want to have to read.
I have up to there. The only part that I didn't get was where you went from that integral to ln, because like, did you just change it?
Okay. Well, that's easy to answer. That's just a pre-existing formula. Yeah, that's just listed here. Let's take a look. That is, let's see. It's either 28.4 or 28.5, where it gives us the formula for the integral of secant. Where is it? Somewhere here. Here, no, I almost found it, not quite. Here it is. Okay, here it is. It is page 861. Yeah. Okay. So it's just a formula that they list for you.
Sounds good. It wasn't on our formula sheet, so I was trying to find it, trying to figure it out, but I.
Oh, okay. I'm sorry if it's not. It should be. Maybe I ran out of room or something, or maybe I didn't include the more rare trig formulas.
Maybe before, say, like a test, if like we're just make sure like on a test, like if we do get something like that, we have a formula sheet that covers everything that we might need on a test.
Let's just quickly check assessments, or no, not assessments, resources. I'm just going to check formula sheet 28. So we got in the formula sheet, we got a bunch of identities. We got basic trig formulas. So I see sine, I see cos, secant squared, cosecant squared. Yeah, it's included there. In if you look other trigonometric formulas, it's on the right. It's the first one on the right.
Oh, it's on the formula sheet, chapter 28.
Yeah.
Okay, I've been referring to the other one. Okay, thank you.
No worries. Yeah, there's the derivative and integration formula sheet, which is just like something I got off of Google. But this formula sheet is specific to chapter 28. So this one's good as well. Let's see. Let's go back to the whiteboard. Okay, does anyone have any other questions about this one or these in general? Because they're definitely pretty long at the very least. Okay, let's do the last one. Let's get rid of this. Okay, and let's just write down what the chart says. So square root of x squared minus a squared, that's the third row of the chart. It tells you to use the substitution x equals a secant theta. And then it tells you to use the trig identity secant squared theta minus 1 equals tan squared theta. Okay, so the question is example number 3. It says integrate the integral of 2dx divided by x, and then you get the square root of x squared minus 9. Why do they have to put that 2 in there? Just makes our lives more difficult. You know, we just got to take the 2 out of the integral, and then it just sits there, and then you got to write 2 over and over again. Geez, guys, come on, make it easier for us. Okay, so for this one, that's like literally the most minor complaint anyone in history could ever come up with. Okay, so let's look at the substitution. In this case, we have 9 for a squared, so a will just be 3. So we're going to use x equals 3 secant theta. And now we figure out all the individual stuff that's in there. On the bottom, you have x, which we just established, so don't have to worry about that. Let's do the square root part. Let's get that over with. Square root of x squared minus 9 is equal to square root of, so this will be 3 secant theta squared minus 9. And now we do something similar to the previous one where we can do some factorization. So let's just distribute that square to the 3 and to the secant. So you'll get 9 secant squared for that little part. And everything else will just stay the same.
How did you get 3 secant theta?
Sorry?
How did you get the 3 secant theta?
So in this case, it's just listed in on page 876. It's the last row where it gives you like a list of these substitutions. So the form is x squared minus a squared. So in this case, the a squared corresponds with 9. So a is just going to be 3. So that's why I use 3 in that case. So whatever number is in the integral, you use the square root of that for a, kind of similar to previous stuff we've done. Okay, so distribute the square. So 3 squared is 9. Secant squared is secant squared, I'm pretty sure. So 9 secant squared minus 9. And now let's factor the 9 out. Maybe in this case, I'll just kind of combine 2 steps into one. Let's factor it. Let's factor the 9 out and let's split the square root. So we'll separate it as well. So take a 9 out and put that in its own square root. And then the rest of it, without the 9 part, will be in its own square root as well. So that'll just be secant squared theta minus 1. So we took out the 9 and put it in its own square root. Again, you can do that when it's multiplication, but not with anything else. Okay, so this is the square root of 9 is 3. And then you'll notice that now we can use this right here, this identity. Secant squared minus 1 equals tan squared theta. So let's put that in there. You still, at this point, you still got the square root though. So tan squared theta. And I always, whenever I do this to the side, I always include the square root part so that when I substitute it into the integral, I can just substitute in, directly substitute it in whatever we've found, rather than having to deal with the square root as you're solving the integral. I find it easier just to do the whole thing separately, including the square root. Okay, so square root of tan squared is tan. So 3 tan theta. So let's just check that's right. Yep, so far so good. So we have x, we have the square root part. We need dx. So dx equals, so it'll be 3. So what is the derivative of secant? I think it's secant tan. Yeah, secant tan. Yeah, let's do that. Secant theta tan theta d theta. Okay, so this one looks like it's going to be a really ugly one, but then if you do it properly, stuff always cancels within the integral. Okay, so now let's just substitute everything in. I'm going to take the 2 out and move it outside the integral. There's no point in really having that 2 in there. So 2 integral, and now let's put everything in. So dx on top is 3 secant theta tan theta d theta. On the bottom, we have an x. That's just 3 secant. That's just our original substitution. And then the whole square root part, like I said, we figured that whole part out. That's 3 tan theta. So this looks like an absolute mess, but some stuff will cancel out. Basically, everything cancels out in this case. It's very interesting how it ends up. So cancel you have a 3 secant and a 3 secant. You can cancel those. Goodbye. You have a tan and a tan. You could cancel those. There's a, oh, sorry, the 3 on the bottom, there's nothing to cancel that. So that remains there. Sorry, I accidentally put the dash line through the 3. But you can only cancel it if there's a corresponding 3 on the bottom or on the top, and that was already canceled because there's a lot of 3s in here. Okay, so that's a weird one. So all we have in the integral is d theta, and then there's a 3 on the bottom, which doesn't really concern us that much because we can just take it out of the integral. So let's just take it out of the integral. and we'll just put it along with the 2. So it'll be just 2/3. And then the integral itself, literally the only thing left is just d theta. So this is virtually the easiest integral to solve because the d and the integral part by definition cancel each other out. Or not by definition, but it's called the fundamental theorem of calculus, and that just states that basically integrals are antiderivatives, and that was established by Isaac Newton. So you can literally just cancel this, and you get 2/3 theta plus c. So again, we run into the same problem as before, that our answer is not in terms of what the original variables are. But this one's a weird one because all of our previous answers involved, go ahead. Someone has their hand raised. Oh, unless it was an accident. Okay, no worries. Let's see. Okay, so 2/3 theta plus c. So yeah, the weird thing here is that there's no trig function in the answer. Typically in the previous ones, there was an actual trig function in the answer. Therefore, we had to construct a triangle and go through all this hassle and then put that in our answer. In this case, there's just a theta. So it's a bit confusing as to what you should initially do. It's like, what the heck am I doing? It's just a theta, like what's going on? Well, let's just go back to our original substitution. In this case, it actually just ends up being easier. So x equals 3. So when in doubt, go back to the original substitution that you stated. Okay, x equals 3 secant theta. So in this case, we'd like to solve for theta in terms of x. Well, this one doesn't require any special triangle. All you have to do is just, first, let's just take the 3 and move it over and change it to division. So you got secant theta equals x/3. And then what you do is you just apply the inverse secant function to each side, and then you get theta by itself. So you don't have to do any triangles. You don't have to really do anything super complicated. You just use an inverse function, because if you apply the inverse secant function to each side, on the left side, they'll cancel each other and they'll just become theta. So let's do that. So left side will just be theta. So imagine that we're applying the secant inverse to that, but that would be awkward to write. So let's write theta. And then also apply it on the right side. So secant inverse of x/3. And so that's what you get for theta. So when there's no trig function in the final answer, it's a bit different, but it's a lot easier to solve. And let's put that in our final answer. So we got 2/3. And then theta is secant inverse of x/3 plus our constant. So it looks like that will be our final answer. I don't see any way of simplifying that. Some people would try to take the 3 out of the secant inverse, but you can't do that when it's plugged into a function. So that there's nothing you can do in this case. So that's our final answer. So hopefully everyone sees kind of the pattern that these use. So I'm going to give a participation question. In this case, that makes sense because there's no assignment for this section. And for the test, it'll just be, I can't remember, but it'll either be like, maybe it's a bonus question or it might not be on the test. I probably shouldn't tell you that, but yeah, it's just such a long question to put on a test. I don't want everyone spending an hour on one question. So we'll do a participation. I have the questions, but I don't know which are the longer answers or harder answers. So I'll just pick one. Okay, so this is participation number 4. Number 4. And this is, so page 878, number 9. And it is the integral of square root of 1 minus x squared dx over x squared. And here, I'll give you a hint for the substitution. I mean, it is in the chart, but regardless, So 1 minus x squared is in the form a minus x squared. So square root a squared minus x squared. So that's just the first one. Yeah. So it's in the form square root. So this is just a hint to get everyone started. Square root of a squared minus x squared. That's the form that this is in. So you use the substitution x equals a sine theta. And a in this case just corresponds with 1. A squared is 1, so a is 1 as well, because again, 1 squared is just itself. So kind of trivial in this case. So x in this case is just going to be 1 sine theta, also known as sine theta. So that's the particular substitution to get you started on it. Okay, I guess that's everything. So I'll put that in writing and I'll activate Dropbox. If you haven't submitted assignment 1B, please do so like very quickly, like within the next hour. And then for the test, we should decide on a date for that. So next Tuesday, we are taking up assignment 1C. And I think we should do the test on a Thursday. It kind of makes sense, but I think next Thursday would be too soon. So let's do it on Thursday, the 14th. And hopefully that's not reading week, because I can never remember when reading week is. So we'll tentatively schedule test number 1 for Thursday, October 14th. And basically I think what we'll do is I'll just send it to everyone online, because obviously everyone at Confed will be getting it online. So everyone can just stay home. I'll email you the test. You have access to whatever you want. You got your formula sheets, you got whatever, it's open book, open computer, and then everyone will just send the test back to me within 2 hours, and I'll just activate a Dropbox after I send the email. So yeah, that'll be a fair way of doing it, because it would be kind of unfair to have some people like supervised and some unsupervised, so we'll just do it all online. So yeah, for the North-based students, don't bother coming in on the 14th, but be ready for the test, and of course we'll discuss that as it comes closer. And then so that's in 2 weeks, and if we run out of review to do, we could always just move on to the next chapter. Okay, so that's it. Does anyone have any questions? Okay, let's stop sharing. So everyone seems pretty good. I still see a hand up, but I think that might just be a mistake. But if you do have a question, let me know. What else? Okay, so I guess that's everything. So everyone, thank you for coming, and I will see you. Have a good weekend, and I'll see you next Tuesday. Have a good one.